through a warehouse in the Chinatown district of lovely Tucson, Arizona, we stumbled upon 4 episodes of the unedited series of Preparing for Tomorrow, a series of informational and instructional videos dating back to the 1950s. This reflects a period in which the world was in turmoil, and citizens of the United States had to be prepared for anything. In total, there were 28 episodes produced, and while the rest of the episodes have mysteriously disappeared during Operation Paul Bunyan, the FBI Art Crimes team has been investigating the possible whereabouts of the lost episodes for several years. Donations to the search can be made to P.O. Box 42609. While watching, remember that these episodes originate from a bygone era and are a part of history themselves. Please enjoy.
War, Hitler, Stalin, Mussolini, plagues on the world, and while they may have been eliminated, our world is still unsafe from evils. The Soviet Union has been advancing their ideals throughout the world in a campaign to end capitalism forever. World War II ended in victory for the United States thanks to the newly developed atomic bomb. However, we are no longer the only nation with access to such destructive weaponry, but have no fear, good citizens of the United States. As we must be prepared for anything, here we will be showing you that there are ways to remain safe in the event of a nuclear disaster. Take a look at this normal American neighborhood. Simple people going about their simple lives, forgetting that the massive weight of a potential nuclear strike holds heavy on their shoulders. The only one prepared for the strike is Linda Parrish, the local neighborhood preparedness coordinator.
Oh, Miss Parrish, I'm quite concerned for my family's safety. I'm horribly concerned that the Soviets are going to drop the bomb. I mean, Newcastle is a target zone for Soviet weaponry. I mean, we do take great pride in that. You're the neighborhood preparedness coordinator. What can I do to keep my family safe? Oh, Mrs. Stevens, I'm glad you came to me for some tips on how to survive a nuclear fallout situation. Waves, or the fundamental units of radiation, have very unique properties that we can track and use to our advantage. See, if we understand the properties of waves, we can shield ourselves from anything the USSR might throw our way. Such as what, Miss Parrish? Well, for instance, there are 2 types of waves, transverse and compression. Transverse is how light travels, and compression is how sound travels. It is strongly advised when you see a bright flashing light, duck and cover. So when you see the bright light from an atomic bomb, you would be seeing a transverse wave. Remember though, if your density were to increase in the medium for which you are viewing the wave, the speed of the light would decrease and you would have less time to shield yourself from the blast. But what do you mean by another medium? Usually, we view light particles through the air, and light waves travel best when nothing impedes their path. When other particles block the wave, the light wave needs to take more time by bouncing off of each individual particle, thus slowing the light wave down, which means it will reach you and your family in a slower amount of time. An example of this would be looking at an atomic blast from under the water of your beautiful pool. Since water is denser than air, the wave takes a much longer time to reach your eye. So, if I'm swimming during an
Oh yeah, you're screwed.
Wait, you keep talking about time for a wave to reach me and my family, but there must be some way to calculate how much time it takes between a blast to reach my family.
Well, yes, there is. I'm glad you brought this up. The standard speed of light is 299,792,458 meters per second, which can then be plugged into the formula speed equals distance divided by time. And if you know the distance between you and the blast, say 3,000 meters, time can be easily calculated for. So, for this example, 3,000 divided by the speed of light, so you can have 0.00010000692 seconds to evacuate. Or, if you'd like the more rudimentary way of determining whether or not you're in the blast zone, just hold your thumb up against where the mushroom cloud from the bomb is, and if it's bigger than your thumb, you're most definitely in the blast zone and you should flee immediately. Remember, you've got all of 0.00010000692 seconds to do that.
Wow, I feel so prepared. Thank you so much, Miss Parrish.
It is not just the everyday citizens that have the weight of an impending atomic attack on their conscience, but the men that run everyday operations of our government as well. They are our first line of defense and need to be prepared for every eventuality when it comes to violence with the Soviets and Khrushchev. Here we see a government scientist, Donald Gripe, hard at work with comrade Craig Strapping, attempting to discover defense mechanisms for a strike that might just hit home. Let's listen in to understand what goes on behind the scenes of the U.S. government.
I think we've covered everything, Mr. Bright. Wild Russian bear attacks, poison in the mustard, and cheese-scented...
Hold on just a second, Mr. Strapping. We have yet to take into account the actual dropping of the atomic bomb, or even the blast radius itself.
But is that truly important, Mr. Bright?
Well, of course, Mr. Strapping. The USSR is most likely to attack with the atomic weapon, and we are tasked with ensuring homeland security.
It does not matter. The U.S. will lose to superior technology.
What?
Excuse me, Mr. Greip. These are the Soviet plane specs that you asked for.
Ah, yes. Thank you, Mrs. Donovan. But could you hang back for a few seconds?
Of course.
Mr. Strapping, take a look at this. Now we know that a Soviet plane can fly at 170 meters per second, and let's say that a bomb lands 4 seconds after it's dropped. How far away would the bomb be from the plane?
Don't Soviet planes accelerate after the bomb is dropped? So we should also factor in that the plane accelerates 2 meters per second squared right after the bomb is released from the plane. But what do these symbols mean? Can you really find the distance between two planes with so little Soviet intelligence?
Well, yes, the delta X stands for displacement in both cases, and we need to find displacement for both the plane and the bomb after 4 seconds, which T stands for.
Isn't horizontal acceleration 0 for the bomb and 2 meters per second for the plane?
Yes, very good, Mrs. Donovan.
That means that V must be velocity, which is equal to 170 for the plane, but also for the bomb. Then, since acceleration is 0, the final velocity for the bomb is also 170, but the final velocity will be different for the plane.
Would you like me to calculate that, sir?
No need. With the kinematic equation, x equals v naught t plus 1/2 at squared, the final velocity does not need to be solved. Now, with all our gathered information, we can solve for the displacement of the plane and the bomb.
The plane is 712 meters, and the bomb is 680 meters, which means the bomb will be 32 meters away from the plane when it reaches the ground.
News for the Soviets. Now, how can we help people out on the ground? Miss Donovan, using your female instincts, what do you think is our #1 concern?
Well, sir, I think we need to be cautious of debris from the bomb and how far it can travel.
Of course, we know on average that shrapnel travels around the velocity of 120 meters per second when it creates a 60-degree angle with the ground, and that would take about 2.5 seconds to do so.
Ha! You cannot simply separate that into horizontal and vertical components.
Yes, we can, using the triangle rules, making the true horizontal velocity of
37.5 meters per second, sir.
Thank you, Miss Donovan. And now we must solve using the kinematic equation as before, which gives us
93.75 meters per second, sir.
Wow, U.S. intelligence and math development is much farther along than Khrushchev predicted.
In light of the recent UFO incident at Roswell, New Mexico in 1947, we bring you this special program of Preparing for Tomorrow, where our psychologist and reporter, Sylvia McLean, brings you face-to-face with one of the eyewitnesses from the incident. Miss Lois Miller, physicist and alien life enthusiast, will be describing to you the phenomenon of the mysterious UFO.
Now, Miss Miller, in your letter to us, you stated that you have some new ideas that will revolutionize the way we think about UFOs and life on other planets. Would you care to elaborate on some of these concepts? Yeah, of course. That's actually why I contacted you. I wanted to tell you all about these epiphanies I've been having surrounding alien life, and I wanted to share it with the world, because everyone needs to know about this. It's super important and life-changing. It all has to do with spinning and rotational motion. That's exactly how they do it. All right. Your eloquence certainly precedes you, my friend. Please, do go on. So do you just want me to talk about the laws of rotational motion?
Well, yes, of course. Please enlighten the audience on just how an aircraft could use rotational motion to possibly fly through the air.
Whoa, that's such a good idea. If UFOs could fly like saucers, that would be insane. But anyways, there are a few main ideas concerning rotational motion, mostly in line with normal kinematics. But mostly, you'll be working with
angular acceleration, velocity, displacement, and time, as we do in normal kinematics.
Okay, so how about forces? How do they play into rotational motion?
Well, they make it spin.
Care to elaborate on the forces acting on the plate?
Well, they're centripetal and they're centrifugal forces. They are less of a specific type of force as much as they are a classification of the way a force, like gravity or friction, acts in a system. When a disk is spinning, there's a centripetal force in the direction of the center of the disk.
Well, what about the kinematics with the plate?
Anyways, see how the saucer is flat and round, like a frisbee? Oh, like a frisbee! Oh, anyways, yeah, like if a glass saucer were a frisbee, that's how they would work, because of rotational motion. You see, rotational motion is simple. Things spin, and you measure them. It works just like normal kinematics and dynamics. Actually, it's different in a lot of ways, now that I think about it.
Fascinating. So how would you suggest that the frisbee-like movement relates to UFO sightings?
To be honest, I'm not really sure, but it sounds super cool, right?
I suppose so.
The toils of the everyday housewife can be a real challenge these days, with new technology around the corner to challenge your skills as a productive worker. There are many do's and don'ts on how to approach this technology, and we have Richard Alistair here to show you just what those are. And remember, it often may take women a longer amount of time to understand the same concepts as men. And if things look challenging, do bear with us. You won't be sorry.
Ugh, I wish the laundry would just stay on the clothesline. It's so frustrating that there's no better way of doing this. I wish I understood how this darn contraption worked.
Don't you worry, Joyce. All you needed was the access to this little piece of technology right here. This is called a hanger. See, you just hang it right here, and then you take the piece of clothing and drape it around it.
Well, I could have figured that out myself.
Oh, don't fret, Joyce. All you needed was for a man to come along and show you how to do it.
I guess you're right after all, but I still don't understand. Just how does this whole thing hold together?
Well, because of physics, of course. Specifically because of the laws of forces and dynamics. If you imagine the clothesline as if it were a free body diagram, then you can signify each force acting on the clothesline. You would have gravity pulling the hanger down, pulling the clothing down, and then you would have a normal force exerted by the clothesline here, keeping it up.
Oh, wow!
And the other force acting on it, of course, is tension. As you can see, this is pulling down on the string, and there's going to be a force of tension over here and over here.
Golly gee! I couldn't have done it without a man like you.
Okay, go in, lettuce. Why won't it go in? Oh, what's wrong? Why won't it work properly?
Oh, Pamela, you're such a silly. Let me show you how to do it. First, you have to keep the cutting board level with the table. And then, in order to have the lettuce fall into the bowl, you're going to need to use the cutting board to create an angle so that the lettuce will fall into the bowl.
Gee, I never would have thought of that. You're so smart, Richard.
Please, call me Dick.
Sure thing. But how come the cutting board has to have so many complicated things?
Well, Pamela, that's because of the laws of physics. And in this case, we're talking about forces and dynamics.
Well, I'd sure hate to break the laws of physics.
Well, first off, you have to realize that when your lettuce is sitting level on the counter, there are a few forces acting on it despite the fact that it's not moving. Pulling downwards on the lettuce is the force of gravity, and it's pulling it downwards, and because of that, we know that there's an equal and opposite force, which is the normal force exerted on the lettuce by the cutting board.
But what happens when I move it up?
Well, Pam, not like that. You move it like this to create an angle. And when you create an angle like that, There's also a frictional force acting on the lettuce going that way. And when you tilt it like this, you're creating more of a gravitational component traveling against the frictional force, and eventually that gravitational force breaks the static friction force and goes right into the bowl.
Wow! Thanks, Dick!
No problem.
Well, I need to plug this toaster in order to make a nutritious meal for my husband. Ooh! Yay! I found an outlet! But is it on? A fork. Better stick it in to find out if it works or not.
Alright then. Whoa, hold it there, Myrtle. You're conducting some pretty dangerous activities there.
What are you talking about?
That there is a good way to get electrocuted, Myrtle. Metal conducts electricity, and the voltage in that outlet is enough to fry your circuits.
My circuits?
When a large amount of electricity flows through a person's body, it can seriously injure you, Myrtle.
Oh no, I don't want my circuits fried. But Richard, electricity isn't alive, so why does it move?
That's a great question, Myrtle. Electricity is composed of tiny particles known as electrons, which have a negative charge. Electrons also have an opposite particle called protons, which have a positive charge. In the world of electricity, opposites attract. Protons and electrons give off electric fields, which flow from the positive to the negative.
Dick, you still haven't explained anything yet.
Whoa there, Myrtle. I'm getting there. The electron field allows for electrons to move. Unlike the electron field, electrons move from the negative to the positive. And remember, Myrtle, only electrons move and not protons.
It's like the swimming.
You got it, Myrtle. It is technically called the sea of electrons. There is also two ways to transfer charges, inductive and conductive. Conductive is the one you were just about to experience. When you stick a fork in an outlet, electrons can easily travel up into your body. When you take the fork away, both final charges will be equal to the two charges of both objects added together and then divided by 2.
Then how does induction work?
Induction works when an object of a specific charge is held to another item of a different charge, which will then move the electrons away to the former object, thus inducing a charge on the latter object.
Wow, brain blast. That'll sure teach me to stick forks in electric sockets.
Okay, I need to toast this bread. It's all plugged in. Now all I have to do is put the bread in the toaster. Wait, why is this bread not toasted? I know I did everything right.
Well, almost everything, Betty.
Dick, why are you here? I can figure this out on my own.
Well, sometimes you need the touch of a man to get things to work right. Well, Betty, if you look at this toaster here, you'll see that you've created a circuit.
Yeah, I know that. It allows for electrons and a current to flow through to a resistor.
Well, did you know that electrons in the current technically flow in the opposite direction? Electrons flow from the negative to the positive, and current appears to flow from the positive to the negative, though current only gives an outlet for electrons to flow. Also, did you know that there are 2 types of circuits?
Well, no.
Yes, they're series and parallel.
Okay, so what's the difference?
Well, in series, current remains the same throughout the whole circuit and voltage is totaled. Parallel is the opposite. Current is added and voltage is constant. Voltage is the ability for electrons to flow and is also called the potential difference.
Well, how do they compare? And how can I use it in the real world?
There are numerous ways to apply this to the real world, Betty. See, the toaster here, well, this is a resistance in the current. And a series circuit you have to set up right now, the only resistance is what the toaster is giving off, making the total resistance equal to the resistance in the toaster.
But is there a way to calculate that?
Of course, the equation voltage equals current multiplied by resistance, also known as V equals IR. Resistance, voltage, or current can all be calculated from the other 2.
I have one more thing to ask, Dick.
Yes?
Help me toast this bread.
Oh, Betty.
Welcome to our final and very special episode of Preparing for Tomorrow. Today we will discuss a very important event in the future that has been determined by some unorthodox methods. Having only enough funding for another week's lunch, we've decided instead to contact a strange person calling themselves the Oracle of Tucson. We were told of an event that will take place over 60 years in the future in the town of Rutland, Vermont. We were given names, descriptions of possible participants in this event, and information on the mastermind of this event, the so-called Mr. Adams. After violently convulsing and shaking, the Oracle recited to us dialogue from the event that we have interpreted for presentation to you, the public, so that the prophecy dubbed AP Physics may one day be dealt with.
I can't spell anything. How do you spell anything?
Well, you're dyslexic. Did you forget?
I'm going to Tufts.
I know.
I'm going to Tufts. Mr. Adams. Mr. Adams, when is the next test?
Gibbard. Oh my god, do you remember that time on The Office when... Look, you're smelly. Andy's over there. And over there. Help!
Actually, Mr. Adams, how many human adults would it take to extinguish the sun?
How we doing? Just gotta send her. I started drinking coffee like the other day, and it's great. It's been a life-changing experience.
Hey, I know the sound electricity makes. Thunder.
Dude, I'm about as lost as a can of tuna fish in the fresh produce section. What's going on?
I have no clue.
Dorks for dork. For being B.F. Skinner, I sure don't know what I'm doing.
Wait, you used to be a magic clown? Respect.
Hey, boyos, you want to see a yo-yo trick?
Dude, gotta comment.
Well, yes, human combustion is technically possible. Well, if you see here, there are many different types of particles, and they have silly names. So this is the emotional spectrum from Green Lantern.
Mr. Adams, when is the next test?
Keep at it, Mr. Adams, but watch out for all those senior tears.